So welcome. So we're going to do two-dimensional motion now, and we're going to talk as there's not many bits to this, but there's a lot of skill involved. So this is something where it's practice, practice, practice. We're going to talk about component equations for two-dimensional motion. We'll talk about component projectile motion. So that's when it's in free fall. And then we'll talk about vector equations for two- and three-dimensional motion. And the final little bit is relative motion. So that's a little bit of an aside, but it's kind of interesting. There's really, you've done all the work for this. It's just basically skill. It's like you know how to comb your hair. Now let's practice, because if you do it right, these become much more straightforward. If your basic skills are not so clear, then it's a lot more. It's like stress testing, you know. Now you got to do components, but in two dimensions, and there's more of them, and you got to visualize better. We know our four equations of motion. We know that Vf equals Vi plus A delta T, and delta X equals a half Vi plus Vf times delta T, and etc. We know those. And what I'm going to say is we're going to use those same equations again. The key thing is, and this is like, if your components are not so clear, the key thing is you can only talk about one dimension at once. You can't have an equation that includes an X component with Y components. It doesn't work. So you got to get used to like discipline of, I only put down X things, I only put down Y things, I keep them separate on my page, I label them. So again, people who tend to do things in their head, they'll look at something, it's not labeled as X or Y, and the next thing you know, they get an X and Y mixed together. So layout, I think, is very important in this. But these are no harder than, they are harder than one-dimensional problems, because often there's two bits, so they're twice the length. And there's how you combine the two bits together can be a bit more intriguing. So they are a step up from one-dimensional stuff. But the basic physics principles are exactly the same as the one-dimensional stuff. So you got the skills, it's just the practice is really what's lacking. So here's an example. Particle starts from the origin. It has an initial, so it starts from the origin. It has an initial velocity of plus 4 meters per second and a constant acceleration of plus 2 meters per second squared along the x-axis. So let's put the velocity is plus 4 meters per second. And let's actually draw the acceleration in. And that's going to be plus 2 meters per second squared along the x-axis. When I begin, I will put that down as equal to V, and that equals to A. But after a while, I suspect you'll be at the stage where you can just look at the units and know which one it is. But it's a good double check to put down what letter you think it is, so you can catch a mistake later on. And then it has a velocity of minus 3 meters per second in the y-axis, and plus 6 meters per second squared along the y-axis. So let me ask you a question. Is it speeding up or slowing down if you consider only its x-axis motion? Speeding up, isn't it? And in the y-axis, which direction is it going now? Going negative, and is it speeding up or slowing down in the negative direction? Slowing down. So eventually it's going to stop, and then it's going to start speeding up going in a positive y direction. Can you see that's inevitably going to happen? You're going to go minus 3 meters per second, minus 2 meters per second, minus 1 meter per second, 0 meters per second, and then plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. So there's a particle, and it's doing these two things. And the way I kind of think about it sometimes is I think about it's almost like you have this football that's been kicked around, and sometimes I only concern myself with the shadow of the football on the ground. And that's my X component stuff. And other times I only consider myself, I have a big searchlight over here, and I only consider myself with the shadow of the football on the wall at the back. So I'm not asking myself about the motion of the football very much. I'm asking myself about the motion of the shadow of the football. Is it the X shadow or the Y shadow? So whatever I do, I've got to break this motion up into X bits and Y bits. That's the methodology. So then I say, okay, what's it asking me? What is the XY position at t equals 5 seconds? Okay, so we're going to find where it is at t equals 5 seconds. So let's start with the X bit. So I'm going to find the position by getting delta X. Delta X means displacement. Delta XX means displacement on the X-axis at t equals 5 seconds using, well, X info. So I'm really clear with myself. I'm only using X info. I look at my diagram and I go VI is equal to plus 4 meters per second. A is equal to plus 2 meters per second squared. Delta T is after 5 seconds. So that's going to be 5 seconds. And I want to find my displacement, my delta X. So that's going to go delta X equals delta X is equal to VI delta T plus 1/2 A delta T squared. That makes sense. That makes sense, doesn't it? So delta X is equal to, let's put our numbers in, plus 4 times 5 plus 1/2 times plus 2 times 5 squared. So this is going to be delta X is equal to 20 plus 25, which equals 45 meters, plus 45 meters. If I start off at the origin, then X pos is equal to plus 45 meters. If I didn't start off at the origin, let's say I started off at plus 10 on the X-axis, then my position would be plus 10 added to the displacement. You see that? Find delta X is displacement, delta XY. If you want to put down delta Y, I'm fine with it. It's just my habit is I don't. Delta X means displacement. At t equals 5 seconds using, and this is going to be Y info. So VI is equal to minus 3 meters per second. A is equal to plus 6 meters per second squared. Delta T again is equal to 5 seconds, and delta X is equal to, I don't know. Same variables, same equation. Delta X is equal to VI delta T plus 1/2 A delta T squared. Dr. B, why are you writing that equation down again? Because I'm learning it. I'm keeping it in my head. You know, I don't want to be worried about this on test day. So delta X is equal to VI. VI is minus 3 times 5 plus 1/2 times minus 10, you see, because I'm thinking about projectile motion. So 1/2 times plus 6. Sorry. Plus 6 times 5 squared. So delta X is equal minus 15 added to, and this is going to be 3 times 25 is plus 75. So delta X is going to equal plus 60, I think. So Y position, this should be delta XY, except Y position is equal to plus 60 meters. So my axes are plus 45, comma, plus 60, comma, meters. Oh, plus 45 plus 60. So that would be D, wouldn't it? Yeah. Yeah. Cool. So it's just longer version of what we did in this case. We're going to see some more, I guess a little bit more intriguing. But I was careful to separate my x's from my y's. I was careful to write down what I did. If you look at how many lines of math there are here, the reason why there's so many lines of math is because I want to be able to come back to this and say, well, I think the answer is 45 and 60. There's 45, there's 60. That makes sense. Where did that 60 come from? I had minus 15 plus 75. Where did that minus 15 come from? It was minus 3 times 5. Where's that? So minus 3. Oh, there's my minus 3 on my diagram. So I can check it. And try and check it. I try and check them backwards, to be honest. Does it make sense? Does this line make sense based on the one before? Because if there's a mistake I'm running into, I go the same direction. If I try and rework the problem a second time, I'll probably make the same mistake a second time. So I'm interrogating my solution. By me writing all this stuff down, me checking my answers is a piece of cake. Now that comes because I'm kind of practiced in the layout. I'm practiced in this. And my advice is, if you want to make fewer mistakes, get practiced in this. You do far harder things every day of your life, but you practice them. So practice this. Okay? Let's make it a bit more interesting. So we're going to go to projectiles. Projectile is a two-dimensional thing that's in free fall. So we talked about free fall in one-dimensional stuff. We could have talked about a vertical projectile. That would have been equivalent. That's also a good language. But more commonly, most projectiles get fired at some angle. And so let me give you the good news and the bad news up front. From my point of view, as a test writer, what is at my disposal? I can have you kick a football across a field. I can have you kick a football off a mesa. I could have you kick a football onto a mesa. I could have you kick a football into the side of a mesa. I could have you kick a football from one tall building to another tall building. I can roll the football off a mesa. I could fire the football down. I didn't draw that very well. Fire the football down from an angle from the mesa. I can tilt my cannon downwards. They're all the same problem. They're all approached in exactly the same way. So they are all equivalent. But if you try, just remember, I remember how he did that one. Does that tell you how to do that one? I don't think it does. I think it's a good, it's a good first cut, but you need to remember the approach, not the line by line. It's the approach you need. And I know that's sometimes hard. Sometimes we get here by learning line by line. And sure enough, the same question comes up, and it's like, oh, okay, I learned it line by line and it worked. And it's very hard if you're used to just memorizing. It's very hard to let that go. But if you want to be an engineer, you've got to let that go, because there's too many problems. You will not be able to. That strategy is going to fail. So you've got to put your effort in where your effort will pay dividends, and that is, why is he doing that next line? Why did he pick this? Because the math is trivial. You can do the math. This is not. It's not the math that's going to limit you for the most part in this course. 99% of people, it's not the math. They do the right math on the wrong problem. They'll often give me back what was in the homework. They'll give me this example, and I'm asking for something different. So really try and let that go. And you're not going to let it go the night before the test. You're going to let it go now and get comfortable with it. But you need to let that go. So what does the free fall bit do? A projectile is in free fall. That means that only the acceleration due to gravity is only the force of gravity acts on it, so it vertically has the acceleration of gravity. So air resistance can be ignored. Acceleration is not greater for heavier objects. So a light object, a really heavy object, and a person all fall with the same acceleration. I prefer 10 now. This was back in the days when I was a bit of a purist. But it makes life so much simpler to use 10 than 9.8. Your math becomes so much easier. So I prefer 10. You're 2% out. You know, have we ever been 2% close in the lab? It's like it works fine. A projectile follows a two-dimensional path. That is a parabola. That's the technical term for it. The acceleration in the y-axis is minus 10 meters per second squared, just as in free fall. The acceleration in the x direction is 0 once the object has been fired and has left the firing device. We can only use these equations when there is a constant acceleration. So you can't include the bit while it's in the gun or the bit while the foot is still touching it. That's not part of this equation. And you can't include the bit once it's touched the ground. So by dint of the math, we can only talk about the flight of it. So sometimes people will bring in perceived knowledge from once it's hit the ground. Yeah, it stops once it's hit the ground, but that's a different journey. In the free fall bit, it hadn't stopped. And they'll talk about, well, there must be an X component because you kicked it sideways. Yes, while I was kicking it, then there was a horizontal force. But once it leaves my foot, there's no horizontal force. So the acceleration horizontally is 0. So people get confused with a conceptual. And hopefully you did some of this in conceptual physics so that got ingrained. Because if that's not ingrained, it'll slip in when you're stressed out. So really, as I say, this course is not about math. It's about the visualization and then the application of math. We must consider the projectile's vertical component of motion independently from its horizontal component, just like we did in that last problem. Projectile travels sideways for as long as it was above the ground. If you think about it, what determines the end of this journey is when this thing falls into the ground. It's traveling nice and steadily sideways for as long as it can, and then it hits the ground. So it's the time, more times than not. It's the vertical journey which is going to determine how long your journey lasts for. Now, they're both interdependent, but, you know, mathematically, strategically, you're going to probably look vertically more often than not. There are some questions where you have to look horizontally to get the time, but they're kind of like a little bit, they're just depending on what information you get, but they don't come up very often. By and large, it's the vertical information you need to get the time. Projectile travels sideways for as long as it is above the ground. The vertical axis governs the duration of the journey, for the most part. You know, I'd say 9/10 of the time for sure. That's you can bank on that 9/10 of the time. So here's an example: we're kicking a ball, or throwing a ball, or firing a cannon, or whatever. Ball X is kicked from level ground at an angle of elevation of 30 degrees above the horizontal. Notice that language. Angle of elevation is elevated above the horizontal of 30 degrees. Air resistance can be ignored. I could just say it's a projectile, and that means that air resistance can be ignored. With what angle will it approach the ground? We need to have a go at that, because that's actually, you don't need to do much, you don't have to do really calculations for that. What do you think conceptually the right answer is there? So just click it in. It's like, got a question or a comment? Or stretch in? Stretch in. Oh. Yeah, okay. That's how we're doing. Come on, just let your gut go. Just have a go and say, what's the worst that can happen? You get it wrong and you go, oh man, my gut needs to be adjusted. Maybe I'm hungry. You know, it's like, let's have a go. What's it going to be? Is it going to be slightly more than 30 degrees, slightly above 30 degrees, or is it going to be exactly 30 degrees? For this idealized case, this is what all we deal with is projectiles are idealized. There's no air resistance. There's no air drag. The problem is we live in a world that's full of drag. So, got to be careful. I'm going to give it just a couple more seconds. Stop it. And so look, most people saying B, a couple of A's, a couple of C's. Let's have a look at that. So what's going on here? Well, there's a lot of symmetries. When you get no air resistance, there's a lot of symmetries. If there was air drag, I'd expect this thing to slow down and it would fall short. So that angle would be greater than 30 degrees. It's hard to see how it would be longer than 30 degrees, but if there was a bit of lift in the object, maybe they would be a bit like that. But this is none of those. They all depend on air resistance. There's none of that. This is a very idealized form, so there's lots of symmetries. So if that's 30 degrees, that is exactly 30 degrees. So it would be that. So there's symmetries that you're not told about that you're expected to know. These might come up in later questions, in which case we'll just do them. But symmetry says that speed there is the same as that speed there. What that means is that the vertical component is equal and opposite to the vertical component. So the vertical component up at one level is equal and opposite to the vertical component down at one level. We did that with one-dimensional motion. It takes as long to get to the top as it does to get back down again. Whole bunch of symmetries. So this is not just math. There's an awful lot of symmetry going on. Another one, cannonball is fired with a muzzle speed, that's the speed it comes out of the muzzle, of 4 meters per second horizontally off a cliff. What is the acceleration in the horizontal direction? Have a go at that, please. Again, it's not a mathematical problem, it's a conceptual problem. Cool. Come on, let's get a couple more. Come on. 22. Come on, number 22. Come on. Going once, going twice. Stopping it. Okay. What do people say? Mainly C. Little scattering here. Mainly C. So let's think about this. Cannonball is fired with a muzzle speed. So it comes out here nice and horizontally. Muzzle speed 4 meters per second. Says, what is the acceleration in the horizontal direction? I want to know A. Is there a force in the horizontal direction? Not the instant after you leave it until the instant that you land. There's no force in the horizontal direction. No force means no acceleration, so the answer is C on that one. Okay. Certainly not 10 meters per second squared downwards, because that's vertical direction. If you put down 10 meters per second squared downwards, home in, get a highlighter and get used to highlighting the direction, because you're slipping on the direction. Is it horizontal? Is it vertically? And if you put down something to do with 4, then home in on the units, because you're kind of been a bit, does that, when you read sometimes, so I learned to read as a word recognizer. I didn't sound out the letters. I kind of like said, you know, that's ball, that's Tom, that's cat, which works great for 3 letters, but when you're doing, you know, establishment, it don't work so well. You've got to recognize establishment, so this really is a bit of a problem. And you can recognize that's the problem. If you catch it soon enough, you can practice and get rid of that. The tendency is you limp along. You tend not to try and, because recognizing it's a pain and you've got to do something about it, and there's no immediate rewards for it. So you get to the stage where now as a 63-year-old, if I'm reading a book with foreign names in it, I have problems with the foreign names, because it's not like I'm pronouncing your name, you'll correct me. No one pronounces the name for me. So I remember reading this book which had a whole bunch of foreign names in, and I was talking to my wife about it, and she said, you know none of their names, do you? And we looked, and I'd pronounced all the names wrong. And I'd repeatedly pronounced all the names wrong, because I recognized that, you know, I can't remember, Dimitri, I'd call it something else. But I'd always call it something else, because it was recognizing. That's a limit in my sense, and I didn't sort it out. And people do the same thing with units. They just look at units, and they don't figure out what is that unit. They're either blind to them, or they misread them, or whatever. So if you have this tendency, I tend to get accelerations and velocities mixed up, recognize, oh, it's about your reading of the units. If you tend to get your horizontal and your vertical mixed up, and you go back and go, oh yeah, I meant it to be vertical and it's horizontal, then that's not going to go away until you focus on, I need to be careful with my axes because I'm making the mistake about the axes. Not all mistakes are haphazard slips. Sometimes there's a system to it. And if you can catch that, in a way, that's a really good thing. If you make nothing but haphazard slips, all I can tell you is be more careful. You know, what do you do for that? You just got to be more careful. I might say write more down. But if you have a slip, you always get the horizontal and your vertical mixed up, then I can tell you, hey, this is specifically what you need to work on. So in some ways, systematic problems are better than random problems. Okay. Cannonball is fired with a muzzle speed of 4 meters per second horizontally off a cliff. It takes 3 seconds for the cannonball to hit the sea. What is the final velocity in the horizontal direction? Can you have a go at that for me, please? Okay, we're back. I'm going to pause it here. I'm going to stop. I'm going to see what people say. Mainly D, a little bit of C. That's interesting. So let's look at this. What we're going to say is cannonball is fired with a muzzle speed. So let's visualize. So here's my cannon. It's fired with muzzle speed of 4 meters per second horizontally off a cliff. It takes 3 seconds to reach the ground. Delta T equals 3 seconds. What is the final velocity in the horizontal direction? Oh, yes, it looks like it's a calculation. It's not a calculation. Final velocity is related to initial velocity through acceleration. There's no acceleration horizontally. A horizontally equals 0 meters per second squared. There's no change in velocity horizontally because there's no force horizontally, because there's no acceleration horizontally. So this is a conceptual question, and it's going to be +4 on that one. Yeah? Okay? So looks like a mathematical problem. Give you just enough information that you can go off and start trying to do sums. But if you do the sums on the right bits, then you'll get 4 meters per second for your answer because you're going to have acceleration equals 0. Cannonball is fired with a muzzle speed of 4 meters per second horizontally off a cliff. It takes 3 seconds for the cannonball to hit the sea. What is the range of the cannonball? Do that one, please. So we're back. Let's stop this and have a quick look. So mainly D. Let's see how that came about. So first thing we do is we visualize. So somewhere or other I've got to draw a diagram. This is, let's have a look, +4 meters per second. 4 meters per second. Delta T equals 3 seconds. Cannonball's going to hit the sea. I want to find the range. The range is that. So what do I know? So I say find using hor info. I want to tell myself I'm using horizontal information. Then I look at this and I go, well, VI is equal to +4 meters per second. I go delta T is equal to 3 seconds. Let's have a look. I want to say A is equal to 0 meters per second squared because I'm horizontal. And then I go delta X is equal to, that's what I want to find out. And I'm with that same equation again, delta X is equal to VI delta T plus 1/2 A delta T squared. So that would be delta X is what I want, that's nice, is equal to 4 times 3 plus 1/2 times 0 times 3 squared. So delta X is going to equal 4 3s are 12 plus 12 meters is what I'm getting. Am I right? No. What did I do wrong? Oh, is it my answers keys that are wrong? No. It's D? Oh, it's there. Oh, yes, it is. Good. Yeah. Okay, ignoring that. So, been nice if I put some signs on here, because it could have, I could have some negatives in here, but, whatever. Notice, even for this, I want to get the full points. I want to get as many points as possible, so I don't want to make any slips. So I'm going to have a little diagram. I am going to have my list. I'm going to have my math. The math is the least of it in a way. It's the other stuff that counts. Cannonball is fired with a muzzle speed of 4 meters per second, horizontal off a cliff. If it takes 3 seconds for the cannonball to hit the sea, what is the height of the cliff? Can you do that one, please? So we're back. Let's stop this. So let's have a look. We have mainly E, a little bit of C, and a smattering of other things. So let's have a look at this, see what's going on here. So cannonball is fired with a muzzle speed of 4 meters per second horizontally off a cliff. So here's my cliff. That's 4 meters per second. And delta T equals 3 seconds. And the cannonball is going to do this. And it says, what is the height of the cliff? Oh, okay, so we want to find that delta X. And remember, I'm starting here, and okay, this is a vertical thing, isn't it? So I say, find delta XY, that's my Y component displacement, using, so what am I going to use to find a Y bit of information? I'm going to use Y information. So from the very get-go, I've got to know which direction I'm playing with. And we've been playing with the X so far, but now we're playing with the Y. So it's not hard, it's just a different direction. What do I know in terms of my Y direction? Well, in terms of my Y direction, VI is not equal to plus 4 meters per second. That's horizontal. VI equals 0 meters per second because you got fired horizontally, which wasn't a little bit up, it wasn't a little bit down. There was no vertical component when you first began. So that's 0 meters per second. And I know my time for my journey is equal to 3 seconds. And I want to find my delta X. And call it delta XY if you like, if it matters. And I know my acceleration, of course, is minus 10 meters per second squared. Then I say, let's have a look. Delta X equals VIT plus, it's the same equation. Delta X is equal to VI delta T plus 1/2 A delta T squared. So mathematically, this is not particularly harder. I'm trying to find delta X this time. And VI is going to be 0 times 3 plus 1/2 times minus 10 times 3 squared. So delta X is equal to 0 minus 3 3s are 9, 5 9s are 45, minus 45. So delta X is equal to minus 54, minus 45 meters. So how high was the cliff? Height is equal, height's measured from the bottom to the top, if you like, or it's a magnitude, 45 meters. So let's think about that. That took considerably longer to get our, usual 20 people or so to get an answer. And even then we were split in terms of our answer. And yet mathematically we're using the same equation, which is no harder mathematically. It's the visualization that's the issue. I suddenly gave you a Y component thing, and you got used to thinking in terms of X component stuff. So if you were struggling with that, or it took you longer, or you found it harder than the previous one, just double check. Do you have a diagram? Because I think the diagram, there's no way I can think this is X component stuff when I do that. There's no way. I know it's vertical stuff, so that's prompting me. Oh, I'm thinking vertically here. And then, did you have a list? And if you had a list, you know, the list helps me get the equation. And then, so the diagram helps me get the list, and the list helps me get the equation, and then it's just math. And the math is the least of it, really. Just watch out for that. These little side bits that you can say, I don't really need, I think help tremendously. I'm not trying to turn you into saintly people who do the right thing just because it's somehow ennobling. I'm trying to get you more points on a test when you're stressed out. So just slow down a bit and take all the steps, and it'll work out a bit better. Cool. Boom. Cannonball is fired with a muzzle speed of 15 meters per second horizontally off a cliff. It takes 3 seconds for the cannonball to hit the sea. What speed? What is the speed of the as it hits the water? I'm going to do this one. It's a bit long, but I'm going to do it. So let me have a look at this. So here's my cannonball. Actually, it's not that long, but let's have a look. This is plus 15 meters per second. The cannonball is dot, 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 dot. Now, at the end, just before it hits the water, it's going to have a x component of velocity and a y component of velocity, vx, vy. And I want to find the speed, and the speed is kind of like speed. That's what I'm trying to find. Okay, that little bit at the end, yeah? Okay. Find Vx using HOR info. Can anybody just tell me what Vx is? What is Vx going to be? Vx here, what's Vx going to be? It's going to be plus 15 Vx final is equal to plus 15 meters per second, because it's no acceleration. So the horizontal velocity never changes. It's always the same no matter what height you're at, because there's no acceleration horizontally. Well, that was easy. Find Vy final using, well, I'm going to use vertical information for this. So now I'm thinking vertically. I go Vi is equal to 0, A is equal to minus 10 meters per second squared. That should be meters per second up there. I go, let's have a look. It takes 3 seconds, so I know delta T is equal to 3 seconds. I want to find my Vf. Oh, I have a different equation. Do I? Vf equals Vi plus AT. Yes, Vf is equal to Vi plus A delta T. So Vf is what I want, is equal to Vi, which is 0 plus minus 10 times 3. So Vf is equal to minus 30 meters per second. Let's take these two bits together. Plus 15 meters per second minus 30 meters per second. S is equal to the square root of Vf squared plus Vi squared. I'm telling myself what I'm doing here. So F is equal to the square root of Vf is minus 30 squared plus 15 squared. Notice how, again, the parentheses help me out. They tell me that negative sign is to do with the direction, and so it's got to be squared. It's not the operator. So this is equal to the square root of 900 plus 225, I think it is. So S is equal to the square root of 1125. So S is equal to second square root 1125. I hope I did this right. I'm rushing a little bit. 33.5. Yeah, that looks right. 33.5. It's a magnitude, so I don't need to worry about the sign. Meters per second, put in a box. 33.5. B for that one. Yep. And we're still using the same physical setup. It's like, this is just, any setup can give us so many problems. Oh, wrong way, did I go? Cannonball is fired on a level field with a muzzle speed of 40 meters per second at 30 degrees elevation above the horizontal. What is the maximum height above the field? So now we're beginning to change things up a bit. So this is 40 meters per second, and that is 30 degrees. Find delta x, y using vert info. Vi is equal to, this is where your trig has to just be solid. It's going to be plus 40 sine 30, and that cannot be a challenge for you. You got to get to the stage where you can go, that's 40, that's 30, 40 sine 30, 40 cosine 30. You got to just get those down, because it's just going to come over and over again. It's like, we're going to go to forces, and we're going to be using these components. If you don't have components down, you got to come and see me. You got to practice it, whatever it takes, but there's no way around it. It's not going to work. So that's plus 40 sine 30, and then we're going to have A, of course, is equal to minus 10 meters per second squared. And then I'm trying to find delta x, y, so that's going to be, I don't know on that. And then what else do I need one more thing. What do I know vertically? What is my final velocity? Yeah, v final equals 0 meters per second. So here, I like to put down start there and end there. So again, I know what I did. I don't use the two-dimensional drawing much, because my math isn't to do with the two-dimensional drawing. My math is to do with either the shadow of the ball on the wall or the shadow of the ball on the floor, either the x component or the y component. So do your nomenclature on the components. So then I'm going to say, Vf squared equals Vi squared plus 2a delta x. So 0 squared is equal to 40 sine 30 all squared plus 2 times minus 10 times delta x. So let's have a look. Delta x is going to equal 40 sine 30 all squared divided by, it's going to be plus 20 on there, divided by plus 20, which equals 2. Yeah, bad mistake. I saved myself because I had the parentheses. I was going to cancel that 40 with that 20, but of course that's squared. So delta x is equal to, get your calculator. Let's do sine 30, 40 sine 30. So 40 times the sine of 30 equals 20. Let's square that. So that's going to be 400 over 20, which is 20. So 400 over 20 is 20 meters. So what is the maximum height? Well, if the displacement is plus 20, the maximum height, max height, that's plus 20, is equal to 20 meters. Cool. Let's see what I have. I've got 2 more, okay? Let's have a look. Cannonball is fired with a muzzle speed of 25 meters per second, 4 degrees elevation above the horizon. What is the range? I'm going to stop this here.